This problem asks us to determine all relative extrema, so local maxes and mins, relative maxes and mins, depending upon where you get taught this information. Uh, this time, though, rather than leaving it up to us how we want to do that, they tell us, like math teachers tend to do, you have to do it in this very specific way. They want us to find relative extrema using the second derivative test. Normally, if somebody says to me, find relative extrema, so find local maxes and local mins, I'm going to go through a first derivative test. And the reason that is, for me, if I'm already going to have to take a derivative, right, the first derivative, I don't want to take a second derivative unless I have to, right? Anytime I go ahead and try to take a derivative, that's one more place that I could mess this thing up. So I generally go ahead and just take the first derivative path. But here, as we have already said, we don't have a choice. We've got to go through this process through the second derivative test. So what that looks like, it's going to be very similar. First part of this process, instead of finding the first derivative, we are going to find, of course, the second derivative. So coming through here, we take our f of x, that equals 3x to the fifth minus 20x cubed. We need to take the derivative once. So taking the derivative of this, that's just a bunch of stuff being added and subtracted. So we're just going to follow our power rule. We bring the 5 down. 5 times 3 gets us 15x. Subtracting 1 from the power gets us x to the fourth. Bring the 3 down. 3 times negative 20 gets us negative 60x. And then subtracting 1 from the power gets us x squared. And now we do it again to find our second derivative. So f double prime of x. Again, stuff just being added and subtracted, so another power rule to get through here. So bring the 4 down. 4 times 15 gets us 60x. Subtract 1 from the power gets us x to the third. Bring that 2 down. 2 times negative 60 gives us negative 120. And then x subtracting 1 from the power gets us x to the first. So step 1 of the process complete. We have grabbed our we've grabbed our second derivative. Now what we need to do is go grab our critical values. So we are talking local maxes and mins, and local maxes and mins occur wherever we've got critical values, or they have the potential to occur wherever we have critical values. So local maxes and mins are always a critical value game. So step 2 here is going to be to find all of our critical values. And as we've seen on previous examples, critical values can occur in two places. They can occur whenever our derivative equals 0. That's the one that everybody remembers. But they also can occur whenever our derivative is undefined. And that undefined situation occurs usually if you have a fraction in your problem and you need to concern yourself with where you would get division by 0. The other place is if you've got a closed interval, then those endpoints of that interval are going to be critical values. Here, we don't have a fraction on our derivative, and we don't have any endpoints, so we don't even need to worry about that undefined. So we're just going to do the standard set the derivative equal to 0. So we set the derivative. Remember, derivatives are where we get our critical values from. So we're going to take that derivative and set that equal to 0. So solving this, as soon as you look down at a problem when you're looking to do your algebra and you see you've got a power of 2 or greater on it, 99 times out of 100, you're probably going to end up factoring that so that you can solve this equation. And so here, that's exactly what we're going to do. We're going to factor out whatever we can. So I can pull a 15 out of both pieces, and then I can pull an x squared out of both pieces. And so that's going to leave me with pulling the 15 out of the first one, and then pulling 2 x's leaves us with just an x squared, minus pulling 15 out of that 60 is going to get us a 4, and then we pulled all those x squareds out. The reason that we do this is now that those things are being multiplied, now we can break this up into 2 smaller little bite-sized math problems. So we know that whenever 15x squared equals 0, that'll give us a critical value. And then whenever x squared minus 4 equals 0, that's going to give us a critical value. So you come through now and just do your math to get those x's by themselves. So we'll divide by 15, we get x squared equals 0. Go ahead and square root both sides of that to cancel out that squared, and we end up with x equals 0. That is one of our critical values. And now you're just going to play the exact same game with x squared minus 4. So this time we'll add the 4 over to the other side. We get x squared equals 4. And then we're going to square root both sides of this. And so out of there we are going to get x equals, because we applied the square root, we get x equals plus or minus the square root of 4, which is 2. So really out of here we get 2 critical values. We get one at x equals negative 2, and we get another one at x equals positive 2. So both of those are critical values. From there, we're on to step 3. This is where things change up, right? So up to this point, it looks basically like a first derivative test. We've found our derivatives, we found our critical values. Step 3, however, because they want us to do this using the second derivative test, you are going to plug the critical values into your second derivative. And that is going to tell us what's happening here. So we're going to need to do, using our second derivative now, so using our second derivative here, we're going to do f double prime of, and we'll start with our first one that we found, which is 0. We're going to do f double prime of negative 2, and we're going to do f double prime of our last critical value, which is 2. So when we get our answers out of here, how we're going to be able to tell if they're maxes or mins are by the concavity, right? So remember, second derivatives tell us concavity of a graph. So we'll end up with 2 options, right, that can work for us. So if it comes out as a positive value, then we know that our graph is concave up like a cup. Well, the only place that a critical value can live in a concave up section is if it's at the bottom there, at a min. So if we get a positive value out, that tells us we're looking at a local min. If we get a negative value out of here, then we know our graph is concave down like a frown. And so the only place that that critical value can live, because it's got to have that horizontal tangent line, would be if it's at the max. So if we get a negative value out, then we know that we're looking at a local max. And if you get out 0, then it's not a max or a min. So starting at the top, plugging in 0 to our second derivative, we get out 0 in that situation. So what we see there is that's not a max or a min. That's neither. Plugging in negative 2 to the second derivative, you are going to get out of there, pop it into your calculator, popping it into that second derivative, you're going to get out negative 240. So that tells us that this is concave down like a frown. And so what we know we're looking at here is we're looking at a local max or a relative max. Plugging in 2 into that equation, you're going to get out a positive 240. So that positive tells us that this is concave up like a cup, and so that critical value in the concave up section has to be happening at a min. And so from there, the last step of this is to go ahead and draw out any final conclusions. Sometimes they want you to go ahead and give them what the actual point on the graph is. So you would say to yourself, okay, we know we've got a local max, and then to get the value out, we would have to go ahead and plug that value into our equation. So we would want to know f of negative 2. Remember that those y values, those points on the graph, are points on the original function. So when we go to get our y values out, we plug that back into the original function. So out of there, we would end up getting out, plugging that into the original function, we would get out 64. And so you would say you have a local max of that y value, 64, at x equals negative 2. Doing for 2, you would say at f of 2, plugging 2 back into that original equation, you're going to get out negative 64. And so, final language might look like local min of negative 64. Maxes and mins are always the y value at x equals 2. The x values are always when it happens. The x values are always when the max occurs. The y values are always what that max or min is. And so out of there, we were able to draw our conclusions about the relative extrema using the second derivative test. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.